We design microchips to be computationally perfect, but the moment we try to connect that pristine silicon grid to the outside world, the physical boundary layer refuses to obey our math. To make a chip actually work, electrons need to enter and exit. Engineers have to precisely control the energy barrier those electrons cross at the metal-semiconductor junction. For decades, the math taught to engineers to predict this barrier was the Schottky-Mott theory. This graphic shows the ideal theory. Subtract the electron affinity from the metal's work function to get your barrier height. Looking at the N-type equation on the right, increasing the metal's work function by 1 electron volt increases the barrier by exactly 1 electron volt. This elegant model is the foundation of textbook device design. In experimental reality, it completely fails. When we actually go into the lab and test different metal contacts on a silicon substrate, the math falls apart. This chart shows the expected trend. If the model were perfectly correct, plotting metal work function against barrier height yields this straight 45-degree dotted line. But look at the actual data along the solid blue curve. It remains nearly flat. You can relentlessly increase the metal's work function, but the barrier height refuses to move. The energy barrier is locked. In semiconductor physics, this anomaly is called Fermi level pinning. Instead of the energy bands shifting cleanly to align with your chosen metal, the bands at the semiconductor surface violently bend and lock into a fixed position. Fermi level pinning proves the physical interface is an active, chaotic electrostatic environment that overpowers the bulk properties of the materials we try to connect. To understand why this happens, we have to look at the exact atomic physics occurring the millisecond a metal touches a semiconductor. This diagram illustrates the timeline. Before contact, the metal and semiconductor have completely independent Fermi levels. The moment they touch, electrons surge across the boundary to establish a shared equilibrium. This transfer leaves positively charged ionized dopants, initiating band bending. Ideal theory ignores that real surfaces are contaminated with dangling bonds and atomic disorder, creating interface states. Quantum mechanics dictates no electron states should exist in the forbidden band gap, yet these chaotic states do. Collectively, they act like a massive electronic charge sponge. Returning to our timeline in panel 4, watch what happens when swapping to a higher work function metal. Extra electrons simply fill the sponge. The trapped charge generates an intense electric field, forcing the surface bands to bend until the barrier rigidly locks in place. By intercepting incoming electrons, the charge sponge strips engineers of electrostatic control. The barrier ends up depending entirely on surface chemistry, ignoring the metal. If the charge sponge locks the energy bands, what determines the specific energy level it anchors them to? The answer lies in an electrostatic target known as the charge neutrality level. The charge neutrality level is the specific coordinate within the band gap where the chaotic interface states balance out and become perfectly neutral. As the Fermi level shifts above it, the interface charge is negative. When it drops below, it charges positive. The Bardeen model treats this dynamic like an electrostatic seesaw. If the Fermi level wanders, the interface charges up, creating an electric field that pushes it back toward neutrality. This feedback loop forces the Fermi level to anchor exactly at the charge neutrality level. To measure just how heavily a specific interface is pinned, engineers calculate a mathematical metric called the pinning factor, denoted by the letter S. This spectrum graphic shows the extremes. A pinning factor of 1 means the interface is clean and ideal. A pinning factor of 0 means the interface state density is so high that your choice of metal is completely irrelevant. Every real-world contact is an electrostatic tug-of-war. The true barrier you measure is a weighted mixture of the metal's ideal work function and the stubborn gravity of the charge neutrality level. This physics creates devastating practical consequences for any engineer trying to optimize a modern circuit. This graphic breaks down a standard scenario. Swap your metal contact, and ideal theory expects a clean 0.5 electron-volt barrier change. But applying a realistic pinning factor of 0.2, the actual barrier only increases by 0.1 electron volts. The interface sponge absorbs the rest. Losing 0.4 electron volts of barrier control might sound like a rounding error, but it is fatal for microchip performance. This chart shows the law of thermionic emission. Electrical current density depends exponentially on the barrier height, not linearly. Because of this exponential sensitivity, any failure to account for the pinning factor will choke the current entirely, rendering the chip non-functional. If the barrier height is hopelessly locked by the charged sponge, how do we force current to flow freely in modern contacts? This graphic flags a persistent myth. Doping does not remove fundamental Fermi-level pinning. The actual workaround is brute force, blasting the semiconductor with massive amounts of chemical dopants. This heavy doping leaves the vertical pinned barrier intact, but drastically thins the horizontal width. This graphic of an ohmic contact shows how we exploit quantum mechanics. Once the barrier is thin enough, electrons simply tunnel straight through the wall, completely bypassing the pinned height restriction. This pinning bottleneck destroys threshold voltagers in modern CMOS gate stacks and cripples the performance of next-generation 2D materials. The semiconductor interface acts as its own autonomous entity. True innovation happens only when we stop fighting the pristine textbook math and start designing around the messy reality of the charge sponge.